session, we shall do a quick recap of what we have discussed until now, and then we will get started. So we have covered a lot of ground with respect to the project management methodology, which is usually applied, and we understand that it has 6 phases. Phase 1 is business and data understanding. Phase 2 is data preparation. Phase 3 is model building. Then we have model evaluation. It's not model evaluation, rather I call this as evaluation, because you also need to evaluate whether your business and economic success criteria are met or not. Then we have model deployment. And then we have model monitoring and maintenance. Okay, even using mind map, this is exactly what we have understood. When it comes to business and data understanding, you need to understand business objectives and business constraints. Then we also look at success criteria. In success criteria, we have business success criteria, machine learning success criteria, and economic success criteria. And then we also have data preparation, which is the next phase. But even before we get there, as part of data understanding, you need to collect the appropriate data. So we have primary sources, data sources, and we have secondary sources. So you go collect the data. As part of data preparation, you pre-process the data or clean the data. Data pre-processing happens. Alongside that, you also perform exploratory data analysis and feature engineering. Okay, then we build the model. When it comes to model building, we will be predominantly talking about deep learning. Okay, that is what we will talk about. Just a moment. Sorry. Okay. And while we were talking about the entire flow, we have also discussed about auto EDA. And as part of this, we have discussed about a library called as detail and how do we proceed. Also, in order to understand deep learning algorithm, we need to have basic understanding of math. Some math foundations is extremely important. So we have understood math foundation. As part of that, our focus was on optimization, wherein we discussed about minima, maxima. How do we figure out minima and maxima? Right? That's what we discussed. So this is a roadmap that we have traversed until now over the last two sessions. Today, it's part 3, and we shall look into deep learning primer. So what are we waiting for? Let's get started. Here is the agenda. We will just understand briefly about how the neural network algorithm came to light. What do we mean by compositionality? Very, very important concept. What do you mean by perceptron algorithm and how does it work? Right, the training of perceptron algorithm is what we'll talk about. Then we will spend significant amount of time on artificial neuron, then handling nonlinear patterns, okay. Sorry, while I keep delivering trainings, I keep getting new thoughts, new ideas, so they will fly away within seconds, so I quickly make a note of that. Okay, we will also talk about multi-layered perceptron. What do we mean by activation functions? What are the error surfaces? How does the backpropagation algorithm work? How are the weights calculated when it comes to backpropagation algorithm? With this, I think the theory will be done, and we will get into the practical aspects. Of course, before practical aspects, there will be one more session on all the regularization techniques. Post that, we'll get into weight calculation. Neural network algorithm got what was actually inspired from biological system, and human brain has a lot of neurons, and when human brain can do multiple things with greater efficiency, because if you're driving a car, what do? You'll be talking over the phone using Bluetooth maybe, and you'll be looking at a probably display board, and you'll also be monitoring the traffic. So human brain is intelligent enough to do all these things, multitasking. With efficiency, we do right. So scientists thought, can we have a similar kind of system in the space of machine learning? And if we can build an algorithm which is very similar to human brain, the way human brain behaves, then the machine learning algorithm also will be as powerful as human brain. And that gave rise to an artificial system, biological system, artificial system. And this artificial system is nothing but neural networks. Okay. So the basic unit of information processing is called as neuron. So you have a lot of neurons out there. All those neurons would be interconnected. In a typical human brain, there will be approximately 10 raised to the power 11 neurons. And average number of connections per neuron would be, 1,000 to 10,000. 1,000 to 10,000 neurons would be there. And within a few milliseconds, the communication will complete. Right? For example, if you touch a hot substance, within seconds, You'll feel the heat and immediately, instantly, within a millisecond or a microsecond, you remove your hand. So the communication speed is much slower. Any complex perpetual decision, if you're taking any complex decision, right? Or if you're working on any complex task, if it is perpetual in nature, perpetual means if it is repetitive, if you continuously keep doing the same thing again and again, those tasks can be completed within a few 100 milliseconds. Okay. Within a few 100 milliseconds, that particular task would be completed. Then we have a rule called as 100-step rule. Any perpetual task would not cross more than 100 neurons. And how many brains do we have in a human brain? 10 raised to the power 11 neurons. Those are huge number of neurons. Okay, if you have those many neurons available, and if you know for a fact that any repetitive task will not take more than 100 neurons, what does that mean? That means that as a human, not many people utilize their neurons completely. Okay, they do not utilize the complete set of neurons. So even if you have a difficult task, do not worry. If you continuously keep repeating that, the job will be done. Okay. Next thing is compositionality, which is very, very important, because when it comes to neural networks, you'll have something called as neurons. Okay, in that way, you'll have neurons. And each layer of your algorithm would capture some elements. For example, think about human brain, for instance. What happens is when you look at an image, you might feel that you're able to see the complete object, you're able to see my complete face and the chair, so on and so forth. But the fact of the matter is that human brain first will recognize the pixels within the image, then the edges. So if you have a video, for instance, video would be broken down into multiple images. So each of these are images. And each image would be broken down into pixels. And each pixel value will have some pixel intensity. And these pixel intensity values range from 0 to 255. 0 means black, 255 means white. Okay, so your human brain first looks at those pixels. Then it will look at the edge. For example, say there is a human face in this. Say you're building a facial recognition system. So you'll have an edge. This is an edge. This is an edge. This is edge, edge. All these are edges. And then texton. Texton is some feature of an image. Then you have motive, which is another feature of an image. Then you identify part. Part means eye is one part, nose, mouth, eyebrows, so on and so forth, are different parts. And ultimately, you'll recognize the entire object or the face of the person. Right? This is how it works. So, as a human brain, your brain works based on compositionality. Just a moment, sorry. Okay. So we have compositionality, basically. And when you deal with textual data, all these are unstructured data types, mind you. Videos, images, audio files, textual data, all these are in unstructured format. So when it comes to image, step by step, human brain would understand different components and ultimately the object, like there is a chair, there is a human. Same is the case with textual data as well. When you look at probably a paragraph, human brain intuitively looks at first the characters, group of characters would make a word, group of words would form a word group. Then you have clauses. Clauses means you end with comma or semicolon, etc. And then you'll have sentences, and ultimately you'll have stories. Okay, that's how it works. Then, when it comes to audio files or speech, first you'll have a sample, then spectral band, then sound, then phone, then phoneme, word, entire word is what you hear. This is called as compositionality. And people thought that when human brain behaves in that way, why can't we have our machine learning algorithm behave in a similar fashion? Why can't we have such a such an option? And that gave rise to the neural network algorithm, which has a lot of layers. Each layer will capture one of the elements. Okay, so that's human brain for you as an image. Okay, and the way the human brain works, based on that, people have come up with neural network architecture. Okay. Within deep learning is synonymous to neural networks, by the way. So the way neural networks work is very similar to how a human brain works. If you have images, and if you supply images as input, okay, and this is your input layer. Then, from the input layer, so human brain, when you supply images to this input layer will take the images and send it to the next layer. And this next layer or next bunch of layers are called as hidden layers. They are called as hidden layers because what features they extract is not really known. What information it's going to extract from the images? Would it extract the pixel values? Would it extract the edges? What will it exactly extract? We are not really sure. So that's why they are called as hidden layers. So the first hidden layer, initial hidden layer, would capture low-level details. meaning very minute details like edges. Okay, if you have an image, for example, you have an edge here, you have an edge here, edge here. All these are edges. This is an edge, or maybe intensity values, etc. Right? So that is what is captured by the initial hidden layers, initial set of hidden layers. Next set of hidden layers would capture mid-level features, meaning eye of a person, or nose of a person, or mouth of a person, ear of a person, etc. It will capture the mid-level features. Then the final set of hidden layers would capture high-level details, meaning entire face of the person in that. And ultimately, you have the output layer, and this output layer would give you the final output. If you're building a facial recognition system, it would probably identify the name of the person. Automatic attendance tracking in organizations could be one classic example. Or if it is a shopping mall, just identifying whether the people entering the mall are male or female. Or what is the age group of the people, middle income group, kids, millennials, elderly people who are entering your shopping mall. That makes a lot of sense, because based on that, you can devise or rent out different shops in your shopping mall, so on and so forth. So this is the high level overview. So any neural network, which is a deep learning algorithm, will have an input layer, output layer. In between, whatever layers you have are called as hidden layers. And you can have as many hidden layers as possible. You need not have one hidden layer. You can have 2, 3, 4, 5, 6, 7,000, 10,000, 20,000, 100,000, your wish. You can have as many hidden layers as possible. Hence, it's called as deep learning. You can get to any depth you want. You can increase the hidden layers infinitely. If you keep on increasing the number of hidden layers, if you keep on increasing the number of hidden layers, the performance of the algorithm might take a hit. It might take a lot of time to process and complete your algorithm learning, machine learning learning, or the training part. It would take huge amount of time if you keep increasing the hidden layers. Okay. So now that we have a high level understanding that we have low level features, mid level features, and high level features which are captured, let's spend some more time to understand this. If you do not want to use neural network algorithms, then you can always use your traditional machine learning algorithms. So you have traditional machine learning algorithms, which are also called as shallow machine learning algorithms. Why do you call them as shallow machine learning algorithms? Because on another side, you have deep machine learning algorithms. Okay, deep, shallow. When you use traditional machine learning algorithms like linear regression, decision tree, naive Bayes, or whatever, traditional algorithms you have, when you use those, you have to manually extract the features. When you manually extract the features, for example, if you have an image, you manually try to extract the pixel intensity values. When you do that, it will be time consuming. That's the flip side. It will be time consuming. However, you would know what are the exact features you have extracted. Features extracted are known. You know what features you have actually ended up extracting. Though it is time consuming, this is the best part. And then you can build your traditional machine learning algorithms on top of that data. When it comes to deep learning algorithms, the features are automatically extracted. So you have automatic feature extraction. While we are going to have automatic feature extraction, it'll be fast because you're automatically trying to extract the features. It'll be very fast. However, the features extracted are unknown. Features extracted are unknown. Since the features extracted are unknown, it is that this algorithm is also called as black box algorithm. Okay, this is the main reason why a deep learning algorithm is called as a black box algorithm, because you don't know. You don't know whether pixel intensity values were extracted or whether edges were extracted or whether motif was extracted. What is exactly extracted, you don't know. However, using some data visualization techniques to visualize the outputs of the hidden layers or the activations, that's what you call them, you can to some extent guess on what kind of features are extracted, but you won't be very clear on what is extracted. Okay, next. So this is what I was saying. If you have an image, if you intend to apply your shallow machine learning algorithms, then you have to manually extract the features, handcraft, manually extract. And then you can use one of your simpler classifier techniques, simpler shallow models. However, when you use deep learning algorithms, you supply your image as an input, and this the features from this image would be extracted, and then you move on with your hidden layers, and finally you get an output. But the features are automatically extracted. Okay. Now let's get into the math notation part. So here, okay, let me explain it. Suppose in your underlying database, you have 5 inputs and an output variable. You have your output x1, x2, x3, x4, and x5. So you have 5 inputs. So you have your output variable and you have your input variables. This is your output. And say these are your inputs. If you have 5 inputs in your underlying data set, then in your input layer, you would have 5 neurons. 1, 2, 3, 4, 5. But we also have one additional neuron. What is the use of that neuron? Why did we get that? We'll understand. Using an example. Suppose you have the pink class. Okay. And also, suppose you have yellow class. To segregate these two classes, you need a line. If you can draw a line, that line will segregate these two classes. Okay. When you have this kind of a setup, or if your data follows this kind of a pattern, then it's called as linearly separable boundaries. It's linearly separable. You can segregate it. However, if you have data set like this, and say we have circles. Then to segregate the pink crosses from yellow circles, you can have multiple straight lines. You cannot have a single straight line, but multiple straight lines can be used. And then anything which falls in between belong to pink class. Anything which falls outside, you can say that they belong to yellow class. Right? So these are all straight lines. And what is the equation of a straight line? Y is equal to b plus mx, c plus mx, however you want to call it, or mx plus c. And even when you look at the linear regression algorithms, y is equal to beta naught plus beta 1 x, so on and so forth. So here you have beta, which is actually multiplied with 1. Here you have a b, which is actually multiplied with 1. 1 multiplied with anything is 1. That is the reason you have this additional input, which will be b. And you always multiply it with 1. Hence, you're supplying x equal to 1, x not equal to 1. 1 into b will be b. So b plus w1 into x1 plus w2 into x2 plus w3 into x3 plus w4 into x4 plus w5 into x5. That's how it works. Okay. So this is non-linear, this is linear. Now, all of these are called as weights. All of these are called as weights. And these weights are randomly initialized. Okay, all of these are randomly initialized. And we are talking about a very basic neural network algorithm, which is called as perceptron algorithm, where you will not have any hidden layers, just one output layer, and you'll have a single neuron in the output layer. So you are going to now aggregate all of these. Aggregation function is applied, and usually the aggregation function which is applied is summation. Summation is used. So what you do is b into 1 will give you b plus w1 into x1 plus w2 x2 plus w3 x3 plus w4 x4 plus w5 x5. So you get this. This is the aggregation function. And once you get this aggregation, you move it to activation function. The value that you get, when you multiply all of these, you get some number. That number, you move it to something called as activation function. And there are a bunch of activation functions. We'll get there. We'll try to understand what are the various activation functions. And then finally, you get an output. But let's understand one basic activation function called as step function. This is appearing like a step. Hence, this is called as a step function. Assume that when you multiplied all these things, b into 1 plus w1 x1 plus w2 x2, when you did that, say you got a value as 0.8. So what? Might be a question. So if this value, if the function value is less than 0, then you will say output is 0. Say here, you are trying to predict whether a person will default on the loan or not default on the loan. So this is the kind of data that you have. F of x less than 0. I mean, if this value is less than 0, so output would be 0. Output will be 0 means person will not default. And if this value is, say, greater than or equal to 0, then you will say that output would be 1. 1 means person will default. Okay, 1 means person will default, 0 means person will not default. Okay, so if you get 0.8, it is greater than or equal to 0, so the output will be 1. 1 means person will default. So the activation function will give you some output. Okay, that's your predicted value. This predicted value is also called as true. Oh, sorry, this predicted value. Okay, I'm sorry, I'll take back that word. This is the predicted value. Now you need to compare whether the predicted value is similar to your actual value or not. And actual value is also called as true value. So what you do is, I'll erase this part, this big equation. This part as well. This also let me erase so that it's easier and simpler. Okay. Now that I've erased everything, let me also erase this part. All right. So you take the first row and take all the inputs: age, gender, income, education, loan amount, whatever. Take all those details. Supply those here: x1, x2, x3, x4, x5, all of those to the first row. Pass it through your algorithm. So all these weights will be randomly initialized. Random numbers are assigned. And then you do that multiplication and get the integration. Take that integration and supply it to activation. Then you get the final predicted value. Once you get the predicted value, say your model has predicted that person will default. But when you look at the actual value, that also says that person will default. When you compare these two, that's a correct prediction. There's nothing wrong with that. Now take the second observation and pass on all of these inputs which you have through your algorithm. And when you pass it, okay, you get the integration, right? You have all these weights into those inputs. You get the integration. Take that and pass it to your activation function. And finally, you get the predicted value. Say the predicted value says default. Now, when you try to compare it with the actual value, which is not default, you'll have incorrect prediction. The moment you have incorrect prediction, there will be something called as loss. There'll be something called as a loss function, basically. You'll have some loss. In that way, when you pass each and every observation through your neural network, for all of these observations, you'll get the loss functions. And when you aggregate these loss functions, when you add them up, or when you take an average, when you aggregating is combining. How? By simple addition or average. Usually people take average. When you aggregate this, you get something called as a cost function. So loss function is for each observation. Cost function is for all the observations. Once you get the cost function, I mean, think about it as error. It's not actually, statistically, it's not called as an error, but think about it as an error. So with that cost or loss, you go back and update your weights. Okay, and update the weights. Now, coming forward and doing the prediction is called as a forward pass. With that cost, if you go back and update the weights, it is called as a backward pass. So you have a forward pass, you have a backward pass. The forward pass and backward pass together are part of an algorithm called as backpropagation algorithm. Backpropagation algorithm. Backpropagation algorithm has two steps. One is come forward, do the prediction, and you compare it with the actual values, get the cost function, and go back and update the weights. That's called as a backward pass. And both the forward pass and backward pass put together would be called as backpropagation algorithm. Okay, next. What happens? What updation of weights are we talking about? Let me take one weight as an example and try to help you understand. This loss is loss or cost is for your misclassified entries, incorrect predictions. When when your model does incorrect predictions, you get the loss or a cost. Okay, this is what we get. And let's take one weight. Some weight was, say, randomly assigned. For that, say you got some loss. Some loss, some error, assume. For some weight which was assigned, you got some loss. And usually, the loss function would appear somewhat like that. It will be a curve. So if your weights are randomly assigned, then say this happens to be your loss or cost. What is your goal? Your goal is to achieve the minimum misclassifications, minimum incorrect predictions. So minimum loss or minimum cost is what we want, which would in turn mean we want minimum incorrect predictions. So your algorithm now with this loss or cost, which you obtain when weights were randomly assigned, with that loss or cost, your algorithm will go back and update the weights. So the weights will get updated. So the weights are updated. The moment weights are updated, you will have a corresponding loss. So the loss will get decreased. It will decrease. Once again, with the new weights, these are the new weights now. With the new weight, I'm giving you an example of a single weight, okay? Because it's two-dimensional, it'd be easy for you to visualize and understand. If it's multi-dimensional, it'll be in a different manner. Now what happens is with the new weights, once again, you pass each and every observation through your algorithm and then calculate the loss for each and every observation, aggregate it to get the cost, then go back with that cost to update your weights. So again, you end up updating your weights. So weights are again updated and your loss also will get updated. Once again, with these new weights, take all of your inputs, again, move forward, calculate the loss or a cost, and then again back propagate and again update the weights. And the moment you update the weights, your loss also will get updated. And now, once again, with the new weights, take all of these inputs, do the aggregation, pass it to activation, get the predictions, get loss and cost. And then when you go back and update the weights this time, probably your loss will increase. So your algorithm will stop. I'm sorry. So your algorithm will stop. Because when you once again update the weights, your loss is increasing, it's not decreasing. And this is how you try to reach the minima. Remember, yesterday we have spoken about minimization, maximization. This is a reason. Okay. So within a loss function, which is a curve, function is one equation. Equation, when you translate it into curve, this is how it appears. You have all these minimas. And your goal is to get to a minima, a better minimum. All these minimas are called as local minima. And the minima, which is minimum of all, is called as global minimum. Okay, you have a lot of minimas, but the minima of all is called as global minimum. Yeah, we'll get there. We look at how the weights are updated, what is the formula, all that we will consider. Okay. It's just a high level overview that I'm trying to give. Now, the algorithm which is used to minimize the loss is called as gradient descent algorithm. Yesterday, did we talk about gradient? Rate of change or gradient or derivative or slope all mean the same is something that we have discussed yesterday as part of our math foundations. Why did we talk about our math foundation? For this purpose. Okay. So we have gradient descent algorithm. Now you understand back propagation, right? So, all right. Now let me erase this part. Gradient descent is used to minimize the loss. Back propagation is used to update the weights. But you update the weights with the rationale to minimize the loss or cost. Next. Within gradient descent, there are a lot of variants which are available. One is called as batch gradient descent. Batch gradient descent algorithm. Gradient descent. What happens in batch gradient descent? Let's understand. If you have, for example, 10,000 observations, 1, 2, 3 in that, let's say here, 10,000 observations. If you pass one after another, all the 10,000 observations to your network, and if you get the predicted values, okay, if you get the predicted values, and if you try to compare it with the actual values, you get the loss function. For each and every observation, you get loss function. Here also there'll be a loss function, but loss function will be 0 because that's correct prediction. You take all of these loss functions, and when you aggregate those, you get a cost function. You take that cost function, go back, okay, go back and update the weights so that you minimize the loss. This process or this algorithm which is running behind the scenes, when you take all the observations, pass all the observations one after another through your network, and once you calculate the loss aggregate and get the cost, and then when you back propagate and update the weights, that algorithm which is used to minimize the loss is called as batch gradient descent. In batch, what are you doing? You're taking an entire batch of your training data, passing one after another through your network, calculating the loss, then going back and updating the weights. This is called as batch gradient descent algorithm. Wow, I just got an idea of creating yet another visualization wherein I show each one going through. Okay, good. This is the advantage, right? As opposed to just working on projects, when I deliver trainings, I get these kind of ideas. And let me show you one thing. Just a slight detour, slight different direction is what I'll take. And this is what I got our team created. So here, if you see, this might be an area of interest for you. So you have all your inputs. They will connect to your network, forward pass, loss is calculated. Then you back propagate, backward pass, and update the inputs. Right. So this entire picture gives you overview of you get the data. When you put the data from various sources into database, it's called as data ingestion. Then you have data pre-processing. These are the various steps. Then you have model building. As part of model building, you have this neural network algorithm, loss cost, right? And then these are the various optimization techniques in which we are talking about batch gradient descent, the first one. Then we have stochastic mini batch, we'll get there. Momentum and all that are advanced, we'll not get into that. And then we have regularization techniques. We will talk certainly about regularization techniques. This is must. We need that. We need those. And then we have the model evaluation part of it. Then you deploy the model and finally you get the. Now I got an amazing idea of explaining gradient descent algorithms to people. Probably just this visualization, one after another, show and explain. Probably it'll be easier for people to watch. Okay, anyways. So next thing is you have another variant which is called as stochastic gradient descent. Stochastic means random. So you have random gradient descent algorithm. Okay, here. Randomly you choose some observation. Say randomly you have chosen observation number 5. Take the inputs pertaining to that, pass it through your network, do the prediction, compare it with the actual value. Okay, and say your model predicted that person will default. But when you looked at the actual data, maybe it says person will not default. So you'll have some loss. With that loss, come back and immediately update the weights to minimize the loss. You update the weights to minimize the loss. Let me put it here. Update weights to minimize loss. Minimize loss. Okay, updating the weights is propagation algorithm, minimizing the losses, gradient descent. So you immediately update the weights. Then randomly choose another observation. Maybe observation number 9999 was chosen. Take all the inputs pertaining to that observation, pass it through your neural network and do the prediction. If your model predicted that it's default and actually also it's default, then also you'll have loss, but it'll be zero. Loss will be zero. So it doesn't make sense to go back and update the weights, right? So again, go to the next observation, say one is selected randomly. Take all the inputs, pass it through your network, get the predicted value, get the actual value. If there is a loss, go back and update the weights. In that way, until you exhaust or complete all the 10,000 observations, you would not, basically not stop. Your algorithm will not stop. It will continue throughout. Each time your model is going to go back and update the weights. Each time it is called as one iteration. Each time you come forward, calculate the loss, go back and update the weights. It's called as one iteration. Once all the observations in your data set, when all your observations in your data set go through your neural network, once it is called as one epoch. One epoch means one time all of your observations will pass to your network. So randomly first fifth one was taken, then randomly next 9999 was taken. Come back, go back, update weights. Come forward, go back, update weights. Then randomly one was chosen. Come forward, calculate the loss, go back and update. Then randomly choose another observation, go forward, calculate the loss, come back and update. You keep doing it until all the observations pass through your network. It's called as one epoch. And in one epoch, in batch gradient descent, you update the weights only once. Because what happens in batch gradient descent? You pass all the observations through your network, calculate all the loss functions, and then take an aggregation of that, which is called as cost function, and then one time come back and update the weights. So when it comes to batch gradient descent, in one epoch, you'll have only one iteration. But when you look at stochastic gradient descent, in one epoch, means one time when you traverse all the observations through your network, how many times you're coming back and updating the weights? If you have 10,000, 10,000 times. Because each time an observation is selected, you take your inputs, pass it to your network, calculate the loss, and come back and update the weights. So in one epoch, in your dataset, if you have 10,000 observations, 10,000 times you update the weights. So how many iterations will you have? 10,000 iterations. Because your dataset has 10,000. If your dataset has n observations, then n iterations will be there in one epoch. Okay. Next. We have yet another gradient descent algorithm. Which is called as mini batch SGD. Mini batch stochastic gradient descent. People were like, you're giving me two extremes. One is you're saying take all the observations, once you pass it to your network, calculate loss for every observation, aggregate it to get cost, go back and update the weights. You're doing it once. And you're calling it as batch gradient. On another extreme side of the spectrum, we have stochastic gradient descent, where you're saying take each observation, calculate the loss, come back and update the weights. These are two different extremes. Can you not have another algorithm which works better? And that gave rise to mini batch SGD. And you have here mini batch SGD. In mini batch SGD, you need to decide on what would be your batch size. Let me erase these things. And then you need to define your batch size. Say you define that the batch size should be 1,000 as an example. So all of your 10,000 observations would be divided into 10 different batches. 1 to 1,000 will be one batch. Then 1,001 until 2,000 would be second batch. Then 2,001 until 3,000 would be the third batch. In that way, you have multiple batches. How many batches? If you have 10,000 observations overall, and if you define that the batch size should be 1,000, in that case, how many batches will you have? 10 batches. Now let's take batch 1. This is called as mini batch SGD, stochastic gradient descent. So within this batch, you randomly choose observation. Say you randomly chose observation number 99. Then you take randomly observation number 99, pass it through your algorithm, forward pass, calculate the loss, save it. Then take next, say randomly observation number 2 is selected. You take all the inputs, pass it through your network, forward pass, and for this, calculate the loss function, store it. Then randomly say you have chosen 1,000, observation number 1,000, pass the inputs through your network, calculate the loss function, and until you get all the 1,000, you keep calculating the loss functions. Once you get 1,000 loss functions, you aggregate them to get a cost function. And once you get a cost function, you go back and update the weights. Then go with next batch. Randomly choose observations within batch 2, randomly pass it, calculate loss functions. Once all these observations are passed to your network, you aggregate to get the cost function. Then go back and update the weights. Then take batch 3. When batch 3 is given, batch 2 weights which were updated, those weights only you take, and then move forward. Calculate all the loss, aggregate to get cost, then go back and update the weights. Then when you go to batch 4, the batch 3 updated weights will be there. Keep doing it until all the 10 batches are processed. So classic question here would be, if I have 10,000 observations, and if batch size is 1,000, you're saying that 10,000 by 1,000, you'll get 10 batches. And in one epoch means once your entire data set should traverse through your network. That's called as one epoch. In one epoch, how many iterations will we have? Iteration means once you update the weights, it's called as one iteration. So how many iterations will we have? Yep. Come on, friends. Don't tell me that only one person is attentive. Absolutely. Thank you so much for motivating me. You'll have 10 iterations. A lot of you all are responding. Thank you so much. So within one epoch, you'll have 10 iterations. Okay, bang on, right? So that's about batch gradient descent, stochastic, mini batch, stochastic gradient descent. Oh, a sigh of relief. Yeah. So we will take a break now. And once we are back, so I think 3:16, let's be back by 3:30. Once we are back, we will talk more on what if your output variable is continuous? What if your output variable is discrete and categorical in two categories? What if your output variable is going to have multiple categories? How will the architecture look like and all that? Yeah, and many more. Perceptron, multi-layered perceptron, and things of that kind, we will discuss. Please take a break and come back. Thank you. Okay, I think we should continue from where we have left, and I'm pretty sure you're happy with the visualizations because it's kind of giving you a high level overview in a simpler manner. Okay, so we had a brief understanding of the input, how the aggregation happens, what is an activation function, what is the difference between loss function or cost function, how the backpropagation works, what is gradient descent algorithm, and how do you eventually update the weights. Okay. And this is what we have discussed until now. So we shall now talk further. This is your basic biological neuron and the various components of that. That's just given for your information purpose. You can read it when you find free time. What do you mean by soma? What do you mean by dendrites? Synapse and so on and so forth. Okay, now a guy by name Rosenblatt has come up with an algorithm called as perceptron algorithm. In perceptron algorithm, you will have input layer and an output layer. That's it. And you'll have a single neuron in the output layer. Okay, that is all it is. Right? And this is called as perceptron algorithm. And while updating the weights, go forward, come back and update the weights, something called as Hebbian learning was used earlier. But later on, people thought there are some flaws when it comes to Hebbian learning, and they have gone ahead with delta learning rule. And this delta learning rule is very effective, and this is exactly what is being used today. Okay, and there we go. So we will talk about perceptron algorithm first, and you update the weights. And how do you update the weights is something that we'll talk about. But you randomly initialize the weights. Okay, you randomly initialize the weights, and then you backpropagate and update the weights. How do you do that? Using this formula. New weights is equal to old weights plus eta value. This is called as eta value. And this eta value ranges from 0 to 1. And you multiply it with error and multiply it with input. What do you mean by this? I didn't understand. It's just one math equation and you're naming what all is there in each of these. We will now understand it in detail. Let's take a very toy example. Say you have a data set. Let me draw it here. In which you have an output variable and say you have two input variables. You have an output and you have two input variables. And you have two classes. One is z equal to 0 or the blue class. Blue class. And You also have red class. You have red class. So you have two red classes, two blue classes. And then the inputs pertaining to this would be -1 and say -1. So -1, -1. Then for this, you have -1 and 0.5. Then here you have 1 and 0.5. And then here you have 0.5 and 1. Okay, these are the various inputs that you have. This is a data set. Now, and you know that these points are linearly separable, meaning if you draw a line like this, then you know that the data points which fall towards the right side belong to one class, and the data points which fall on the left side belong to another class. Okay. And when you run your algorithm for the first time, so this is how the particular visualization was appearing. Assume that this is how things work. Just a moment while I try to. Just one more moment. So that I have sufficient space to explain the. Yep. So the reason why I've taken that quick 1 minute time was to ensure that the data is visible. It was just overlapping. So suppose when the weights were randomly assigned, the weights were selected as 0 and 1. There were, say, two weights. I always, use that space so that it's easy for people to understand. So you have to just further allow me a quick moment. I will have to fix a small thing here. One moment, so sorry. Some thing should be done here. Yep. Okay. Yeah. Now I think I'll be. So suppose the weights were randomly assigned in this way. So ideally, what happens? You'll get two neurons, and say you have one output neuron. And then finally, you have an output. because you have two inputs, you'll have two neurons. And since it's perceptron algorithm, you'll have a single output. There won't be any hidden layers. And assume that the weights are selected as 0 and 1. Okay, these are the weights which are given, which were randomly initialized. And assume that the eta value was chosen as 1 by 3. Eta value ranges from 0 to 1. And say you have selected an eta value as 1 by 3. So the new weights is equal to old weight plus eta value into the actual value minus predicted value into input. Okay. Now this is the classifier. Your perceptron algorithm is coming up with this line, equation of line, which would segregate one class from another. Anything which falls below belongs to Z equal to 0 or blue class. Anything which is above belongs to red class or Z equal to 1. So this is below the line. It is actually blue. It will also be predicted as blue. This value which is above is actually red and also will be predicted as red. This is also actually red. It will be predicted as red. But this blue, which is above this line, should be predicted, it will be predicted as red, this point. But this is blue. So there is misclassification here. So whenever there is misclassification, your weights should be updated. So the new weights is equal to old weights. What is your old weight? 0. Plus eta value is 1 by 3 into. You have your actual value minus predicted value. Actually, this is Z equal to 0, blue. But then it is predicted as 1, Z equal to 1, because it's falling above. And 0 minus 1 is minus 1. Into. What is the input pertaining to this misclassified entry? This misclassified entry has -1 and 0.5. So it's this point, which is actually misclassified. So the input is -1. When you solve it, you get 1 by 3, which happens to be the new weight now. So for this, it will be 1 by 3. What about this? So you say new weight equal to old weight, which is 1, plus eta value 1 by 3 into actual value minus predicted. Actually, it is 0, Z equal to 0. But since it's falling above, it will be classified as 1. So 0 minus 1 is -1 into the input is 0.5, which is 1 by 2. When you solve it, you get 5 by 6. So the new weights will be 1 by 3 and 5 by 6. Okay, so these are the new weights. Now with these new weights, when you once again run your model, your classifier is slightly changing, right? With 1 by 3 and 5 by 6 when you run it. Earlier, classifier was like this. Now classifier slightly changed. But still, this data point will still be misclassified. Because this is actually blue color, but since it's falling above, it will be classified as red, which is 1, blue is 0. So for this misclassified entry, you'll have a loss. So you once again have to update the weights. How do you update the weights? New weight is equal to old weight plus eta value into error into input. So new weight is equal to, what is the old weight value? 1 by 3 plus, what is the eta value? 1 by 3 into actual value minus predicted. This is actually z equal to 0. But since it's falling above the line, it'll be classified as 1. So you get minus 1 into the input pertaining to that. One of the inputs is minus 1. When you solve it, you get 2 by 3. There are two weights, right? Because you have two inputs, you'll have two weights. To update the next weight, you take the old weight plus eta value is the same into actual value minus predicted value will give you minus 1 into, here you have 0.5, which is 1 by 2. When you solve it, you get 2 by 3. Okay. Now with these new weights, when you look at your classifier, you get a classifier such that now there are no misclassifications. These 2 points fall below and these 2 points fall above. Job done. Okay, everything is good now. This is how your backpropagation algorithm will move forward, go back, and update the weights. Next. This is what we discussed about. Every neuron, friends, except for your input layer, in every other layer, every neuron that you have will have two components. It will have the integration function and the activation function. You'll have the integration function and you'll have the activation function. Finally, you'll have the output. And then you have linear patterns and nonlinear patterns. Perceptron algorithm is used to handle linear patterns. Meaning, if you have data like this, if you draw a line, if these are the two classes, it's called as linear pattern and linearly separable boundary. And if you have data like this, it's non-linear. It's a non-linear pattern. To capture this nonlinear pattern, there are two ways to handle it. One way is change your integration function, meaning if you have 3 neurons in your input layer and if you have 1 layer in your output, integration, right, is summation usually. If this is x1, x2, x3, of course, you'll also have one bias and weights will be randomly assigned. And what do you mean by aggregation here? The integration function is summation, meaning b into 1 is b plus w1 into x1 plus w2 into x2 plus w3 into x3. That's the integration. And then once you get this value, you move it on to the activation function. And then finally, you get an output. Okay, so if you change this from summation to something else, then it works. So this integration part, if you change it to something else, then you'll be able to handle the nonlinear pattern. This is one way of handling the nonlinear pattern. The second way of handling the nonlinear pattern is using multi-layered perceptron, also called as MLP, or artificial neural network. The classic neural network algorithm. In this multi-layered perceptron algorithm, you'll have perceptron means a single line. If you have multiple lines like that, it is called as what? Multi-layered perceptron. Okay, it's called as multi-layered perceptron. Okay, so when it comes to integration functions, what are the various integration functions that we need to have? One is a quadratic function. If you have a pattern like this, right? If you have data like this, you have data like this, right? So when you want to segregate the pink class from the blue class, you will have a curve like that. That's quadratic function. And then we also have something called as spherical function. If you have data like this. And if you want to segregate the pink from the blue, you should have a spherical shape. That would be captured when you have your integration like this. So this integration function to capture quadratic function pattern, this is a function that you need to use. This theta value is nothing but b bias. That b is given a special name called bias. And you have spherical function. If you have a spherical shape, this integration function, instead of just multiplying and adding, if you apply this, then it works for you. Having said that, so how will your equation look like? Okay, let me first write that. If you have 3 input neurons and 1 neuron here, and if this is the integration, say you have bias, which will always have 1, then say you have x1 and x2, and your weights w1, w2. Typically, how does this integration work? B into 1 plus w1 into x1 plus w2 into x2. Then quadratic function, how does it work? B plus w1 x1 squared plus w2 x2 squared, so on and so forth. This is quadratic function. How about spherical function then? B plus x1 minus w1 whole square plus x2 minus w2 whole square plus x3 minus w3 whole square, so on and so forth. Okay. So rather than for every shape changing the integration function, because if you have multiple inputs, you really don't know what pattern the data follows. So in that case, deciding on the appropriate integration function is difficult. So what do we do then? We can apply multi-layered perceptron, which should automatically learn the nonlinear pattern. It is very similar to an algorithm which is called as support vector machine. In support vector machine, there is a concept called as kernel trick. The different quadratic functions are similar to that, but this is a very tedious task to keep experimenting with various options. Hence, multi-layered perceptron, it will work absolutely fine. The only thing is, there will be additional layers, which will be called as hidden layers. Okay. So if you have your input is given to the first layer, which is called as input layer. Either you represent the layers like this, left to right, or bottom to top, or top to bottom, doesn't matter. Okay. So it's just a representation, I think. So you have the input layer. When you supply your image to your input layer, it will capture some patterns. The patterns which are captured are called as representations. Some representations, some features would be captured. What exactly it is trying to capture, we don't know. But we know that the initial set of hidden layers. Oh, okay, sorry, my bad. This is the input layer. That input layer is not shown in this particular image. And here you have the first hidden layer. This is the first hidden layer. First hidden layer captures what? Low-level details. Then once you get all these representations, you pass it on to the next hidden layer. Next hidden layer captures mid-level features. And then you get all the representations. Then you have another hidden layer which captures high-level details. And ultimately, you have an output layer. And the output layer is giving you the output. This is particularly a screenshot pertaining to recognizing your handwritten digits. So you might have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are all the handwritten numbers. The moment there's a handwritten number in a different way, you or in any manner you write 4, doesn't matter. When you supply it to your neural network algorithm, it should tell you that that number is 4. It should be able to predict. Okay, so input, hidden layer, multiple hidden layers, output layer. That's how it works. Okay. Now, there are plethora of activation functions which exist. Okay, and we need to talk about these. First, we have something called as identity function. Within every neuron, I repeat, apart from the input layer. Okay, so I'll write this once again. That's okay. Suppose you have an output variable and 3 input variables. If you have 3, in the input layer, you'll have 3 neurons, x1, x2, x3, and then you'll also have one bias. And then say you have a hidden layer, one hidden layer. Say you have 2 hidden layers, and then finally your output. And if, or let me put it this way, every neuron, apart from the input layer neuron, will have both the components, integration, activation. Integration, activation. Integration and activation. Integration, activation, integration, activation. Integration and activation, and then finally integration and activation of your output. This is called as input layer. These are your hidden layers. And this is your output layer. Number of neurons in your input layer will always be fixed. Those will be equivalent to the number of inputs that you have. If you have 3 inputs, you'll have 3 neurons plus 1 bias. In hidden layers, number of hidden layers that you can have is up to you. You can have 2 hidden layers as I've drawn here, or you can have 1,000 hidden layers. It doesn't matter, right? It really doesn't matter whether you have 2 hidden layers or 1,000 hidden layers. And it really doesn't matter on how many neurons you need to have in each of the hidden layer. In one hidden layer, you can have 3. In another, you can have 1,000. In one, you can have 100. In another, you can have 2. It's up to you. What does that mean? This means that number of hidden layers and number of neurons in each hidden layer number of hidden layers, number of neurons in each hidden layer is experimental. That means you can experiment with these. You can use any number of hidden layers, any number of neurons in each hidden layer to experiment. So these are called as hyperparameters. What are hyperparameters? Hyperparameters are those options which can be changed. By changing, you experiment your model. Okay. All right. Next. In the output layer, okay, number of neurons that you're going to have in the output layer is also fixed. Like the number of neurons in the input layer is fixed, number of neurons in the output is also fixed. How do you fix that? If the output variable is continuous or count, numeric, then the number of neurons in your output layer will be equivalent to 1. If your output variable is categorical, and if you have two classes or two categories, like whether a personal default or not, etc., then you'll have one neuron in your output layer mostly. You can also have two, but mostly one. If you have categorical data, and if you have more than two classes, like say you have 10 classes, for example, then you'll have 10 neurons in your output layer. So the number of neurons in your output layer, number of neurons in your input layer are more or less fixed. Then what is variable? The number of neurons in your hidden layer is fixed. What is variable? The number of neurons in your hidden layer is variable. My bad. Number of neurons in input and output layer are fixed. Number of neurons in your hidden layer are variable. Number of hidden layers, number of neurons in hidden layers are variables. And within these, you see that activation function, the F activation function. The kind of activation function that you are going to use, activation functions in hidden layers, is also variable. Means you can give any hidden layer, any activation function for your hidden layer neurons. So this also becomes one hyperparameter. There's already one hyperparameter. This is also one hyperparameter. The activation function in the output layer varies. Also varies, but there are certain defined thumb rules. If your output variable is continuous, okay, here, the output layer neuron, output layer activation function rather, is going to be identity function or a linear function. If you're categorical in two categories, then the output layer activation function can either be sigmoid or tanh, usually. And if your output variable has more than two categories, in the output layer, you use activation function as softmax. See, running the algorithm in Python will take probably 10 minutes. All these you define, job done. Automatically, your system will take care of that. But which one should I use? Why should I use that? If you have knowledge about these, things will become very smooth, very simple. That's why we are doing all these things. Okay, next. Every neuron would be connected to every other neuron in the forward pass. In the forward pass, every neuron would be connected to every other neuron. Is that the case? 3, 3, 3, and 3. Okay. 1, 2, 1, 2, 1, 2. So every neuron will be connected to every other neuron in the forward pass, forward direction. And then finally you get an output. When every neuron is connected to every other neuron in the forward pass, okay, then it is called as fully connected network. Fully connected network, or this is given another name called as dense network. Dense network or fully connected network. Dense network or fully connected network would mean every neuron would be connected to every other neuron in the forward pass. This is called as forward pass. And then we also have a backward pass. As part of your backward pass, you go back, update the weights. It's called as backpropagation algorithm, and you minimize the weights. That's called as the algorithm which we use is called as gradient descent algorithm. Okay. Now we will do a small quiz. Okay. And I want you all to resort to your LinkedIn profiles. LinkedIn profiles, please. And let me help you all answer these questions. Okay. So I will start a small pool. Yeah, and my questions are coming up. What are the various gradient descent algorithms? Option 1 is batch gradient descent. Option 2 is stochastic gradient descent. Option 3 is mini batch stochastic gradient descent. Option 4 happens to be okay. Now I have put a poll. Okay, so here is a poll question. Please, can you all answer to this? Yeah, please, can you all answer? Please go to that and please respond. I'll be viewing your results here. And while you answer, I request everyone to please answer. This means that you're active. And what I shall do is, in the meanwhile, I'm going to post another question. Okay. There is also another question that I've posted. Here is, yeah, yeah, you can select only one option. Absolutely. Ah, okay, okay. So sorry, my bad. In that case, I'll just quickly edit that. My bad. Mhm. I'm unable to do that. Yeah. Maybe you can put it on the chat window. So sorry. I'm unable to edit that. I'll say mention in the comments if there are multiple options to be selected. Yeah, I made that small adjustment. You can probably answer that one. Okay, quickly, friends. There are two questions, and I request you all to answer these. Second one also I've posted. Yeah, two questions I've posted. And one final question coming your way. And I request you all to answer. Um, yep. So this is yet another thing. Yep, I posted. I already see the responses coming in. Good. So for the second question, also I request you all to comment. And the third question is being posted here. Yeah, yeah. Please, Gokila, you will have to just answer quickly those questions, and then certainly attendance would be given. Please answer. Yep, sorry. Not really. Attendance would be separate, but I request you all to answer. I just want to see how many of you all are answering correctly, how many of you all are incorrectly answering. Only for my purpose. That has nothing to do with attendance, by the way. Yeah, I just want to see. what you're answering. That's it. Whether you're answering correctly or inappropriately, that's the only purpose, nothing much. Okay, quickly, friends. So you just need to click on that link and answer. There are 3 questions which are there. I hardly see 8 people, etc. respond. There is a tie with respect to one specific question that's very interesting. And majority wins is what I understand. Okay. So we will share the attendance link also, not an issue. Oh, okay. So my question, or I'll share it. You just say A, B, or C. Here is one of the questions, okay? And the question is, how many iterations will you have in one epoch for SGD? A or B or C? Yep. You can use a chat window also on Zoom and answer. Is it A or B or C? Yep. Let's see how many of you all will answer. And the right answer happens to be in SGD, means stochastic gradient descent. And the right answer happens to be C. If in your data set, okay, if you're going to have 10,000 observations, then 10,000 times your weights will be updated in SGD, right? What does SGD mean? Stochastic. Randomly observations are chosen. You take these inputs, forward pass, calculate the loss, come back and update the weights one time. Then again, randomly choose another observation, pass it through, come back, update the weights in SGD. Okay, that is how it works. Let me put 2 more poll questions and I'll stop because, okay, anyways, let me go with this question where there is a 50-50%. The question is, what is the name of the algorithm which is used to update the weights, not minimize the loss? I'm telling update the weights. You have 2 options, A and B. What do you think it will be the answer? Yeah, let's see. You can use the chat window to answer. To update the weights. I repeat, not minimize the weights. Sorry, not minimize the loss, to update the weights. Wow, a majority of y'all are saying it is B, and do you know what? That is the right answer. Wonderful. Now here, what are the various gradient descent algorithms? And you have 4 options, A, B, C, and D. And assume I give you E, which is A, B, and C options. And I also give F, all of the above. Then what answer would you go with? Wonderful. A lot of you all are going with E, and that happens to be the right answer. Okay. So you have batch gradient descent, stochastic gradient descent, and mini batch stochastic gradient descent. All of these 3 happen to be the gradient descent algorithms, which we have discussed. Okay. Hope this quiz helped you. to recap whatever we have learned. And tomorrow, when we connect and when we discuss, right, we are going to have approximately 10 questions, which will also serve as a recap. So, all the best. And there you go. You wanted attendance link. We have given you the attendance link. Please proceed further with that. And I'm also going to share on the WhatsApp the previous sessions, you know, recorded videos. You might want to go through those. Okay.